Mr. Long, the past few days it's been raining so heavily.
Okay.
My umbrella got inverted.
Oh my gosh, Mr. Tim, for someone of your physique so muscular, I can't believe that you can't withstand the wind.
Sadly, I can't.
Anyway, looking at that inverted umbrella, right, it kind of reminds me of what we have studied last week, known as an Sn2 mechanism. Mr. Tim, can you help me share with me what's going on last week?
Yeah, come guys, let's go to the notes, yeah? So, the S in Sn2 stands for substitution, and the N stands for nucleophilic. Now, the 2 does not stand for a two-step reaction. It stands for a one-step reaction with 2 molecules involved in that particular one step. Now, let's bring you through. Again, if the electrophilic carbon in the RX, it is not sterically hindered, then the nucleophile can easily do a backside attack and attack that carbon and break that CX bond, forming this thing what we call a pentavalent transition state, where the CX bond then breaks later to release off your X minus, right? Now, so this is what we call inversion of configuration, guys. If you look at your reactant, can you see how the configuration was at the beginning like this, and at the end, in the product, it looks like this, okay? So this is where our umbrella has just inverted, all right? Now, Mr. Long, what happens if the carbon is sterically hindered, like boarding a train at 5 p.m., peak period?
So definitely it's going to be very crowded, right? I'm quite surprised, Mr. Tim. I thought that you always grab. I can't believe that you actually know the situations inside the public transport. But anyway, coming back to your Sn1 mechanism, as what Mr. Tim suggested, the 1 over here does not really mean that it's a one-step mechanism. In fact, it is a two-step mechanism, but the 1 actually represents just having 1 molecule in the slow step. So our halogenoalkane, in the presence of heat, is going to undergo a heterolytic breaking. The CX bond is going to break automatically to release me a carbocation. Now this carbocation is going to involve itself in step 2, where it's going to get attacked by a nucleophile to give me the product that I want. Alright? Now, Mr. Tim, now if you are a halogenoalkane,
okay,
can you tell me which mechanism would you choose to undergo?
Oh, that's quite tough. So it really depends on whether your halogenoalkane is sterically hindered or it is not. Now, if the carbon in the halogenoalkane, it is not sterically hindered, so we have only 1 alkyl group, so usually primary RXs, then it is very easy for the nucleophile to come in and attack that carbon there. And yes, but if the carbon is sterically hindered and if you have big fat alkyl groups blocking that carbon, then it's very difficult for the nucleophile to come in now and attack. So this is exactly when no more backside attack happens, that CX bond now breaks heterolytically, right, to give you that carbocation, which is stabilized by your electron donating alkyl groups, dispersing that positive charge and stabilizing your carbocation. Okay?
Right. So let me summarize this for you. So in general, if you have a primary halogenoalkane, it rather undergoes
Sn2.
Right, and if you have a tertiary halogenoalkane, you rather undergo
Sn1.
So a big number becomes small, a small number becomes big, right? Let's say what happens if you have a secondary halogenoalkane. Mr. Tim, what will happen?
Damn, what, if it's a secondary halogenoalkane, then you really have to think. Because it could be Sn1, it could be Sn2, or it could be a combination of both. We're not so sure.
Right.
So to really know, we need to do an experiment and we have to look at the product mixture. Now, if the product mixture is racemic, then we know it's Sn1. Now, the product mixture has an inversion of configuration though, then we know it's Sn2. Okay? Now, what exactly does a racemic mixture mean? It is this. Guys, I want you guys to focus on the carbon in the tertiary carbocation here. Circle it up for me. Notice with me that the carbon, Mr. Long, has 3 bond pairs, 0 lone pairs. What shape is this?
It will be trigonoplanar, which is flat.
Okay, it's completely flat. Now, which means a nucleophile can attack from the top or from the bottom. Now, there's an equal chance of doing it, which means if the product is chiral, 50% of the product will rotate plane polarized light clockwise, okay? And the other 50% will rotate plane polarized light counterclockwise. Now, in other words, the product mixture has 0 optical activity, and now this is what we call a racemic mixture. Mr. Long, can you bring me through the inversion of configuration one?
So this is very similar to your inverted umbrella, right? So once again, we have to pay attention to the reactants being a chiral carbon. So if it's chiral, it can rotate light. Let's say it rotates clockwise, right? So I'll put this as a plus over here. Now, the moment it undergoes Sn2, we say that the arrow, or rather, sorry, the umbrella is going to now face the other side. So that it's going to be facing in the, will be rotating in the counterclockwise direction. I'll put this as a minus. So there is this opposite direction going on over here. The very technical term that we use is called an inversion of stereochemical configuration. right? Now, let me bring you through the last difference between Sn1 and Sn2, which is to deal with the thing called a rate equation. Now, I'm asking you to go back to kinetics, right? To recall that in order to deduce a rate equation, we always look at the stoichiometry of the reactants in the slow step. So in the context of Sn1, the slow step only uses one reactant. So what do you think the overall order of the reaction will be?
One molecule in the slow step, one, overall order one.
That's right.
Yeah.
So it corresponds to Sn1, and more importantly, the rate equation overall order is 1 as well. Now, how about Sn2? You say that there's going to be 2 molecules in the slow step. So what will the overall order be?
2.
2. And that corresponds to the 2 over here.
Yep.
And in terms of the rate equation, overall order is 2, where each of the reactants, its order is going to be 1. Okay? Now let me link this back into your energy profile diagram at the bottom. Important aspect is the fact that the number of humps that you see in the energy profile diagram will correspond to the number of steps. So Mr. Tim, for Sn1, you see 2 humps because you have
2 steps.
2 steps.
Yeah.
So there's going to be 2 activation energies. Mr. Tim, why is the first activation energy higher?
Because it's slow. If the high activation energy, it takes a bit slower. Slow step.
That's why you get a higher activation energy, right? But for the second one, there's only just 1 step reaction, so you expect to only see a 1 activation energy.